Alright, so let's do a little bit of a warm-up. Let Cn be a cyclic group, and suppose n is even. Then we know that there exists a subgroup that consists of half of the elements. So for instance, suppose n was 6, and 6 cycle here, 1, 2, 3, 4, 5, 6. The subgroup generated by this permutation is the cyclic group of order 6. Then 6 sigma squared is a subgroup of order 3. And so this is true in general whenever you have a cyclic group of order n, and G is a generator, G squared generates a subgroup that has half the order. Similarly, look at the dihedral group, which has even order. The dihedral group also has a subgroup that consists of half the elements. So for instance, let's look at D4, the symmetry group of the square. While the rotation is a 4 cycle, so the subgroup generated by the rotation is a cyclic group of order 4. And in general, the subgroup generated by the rotation has order n. So you could take H equal to the rotation subgroup. And so in these two cases, you have a group of even order that has a subgroup that has half the size of the whole group. So somehow you can separate the group into evens and odds, so to speak. This motivates my question. Look at the symmetric group. Let n be large enough so that Sn, it has order n factorial. When n is at least 2, n factorial is even. Is there a subgroup, H, that has half the elements? Well, let's try looking by example. When n equals 2, well, you've got the identity permutation and then the whole thing, so the identity subgroup works. Okay, that's not that interesting. Let's take n equals 3. The symmetric group has order 6. There are 6 permutations. I wrote them down this way using cycle notation. I left off the 1 cycles here. So it turns out there's exactly 6 permutations. Note, I wouldn't expect students to know how to find them in advance this quickly. This is because I've studied this group way too many times in my life. So you want a subgroup of order 3. Well, you look and you remember that a 3 cycle has order 3, so the subgroup generated by it has order 3, and you can check that that's those 3 elements. So if you take H to be equal to this cyclic subgroup generated by this 3 cycle, you'll get half the elements in the group. And notice what you don't pick. You don't pick these 2 cycles in this case. Well, now let's go the next level up. There's 24 permutations. You've got these transpositions. They're 2 cycles. There's 6 of them. Consists of all the ways you can pick 2 elements and swap them. Then we see that there are a whole lot of 3 cycles consisting of, well, you pick one element that doesn't belong in the 3 cycle in one of 4 ways. And then you put the minimum element in the 3 cycle first, and then there's 2 possible ways to put the next element. So that gives you 8 possible 3 cycles. And you can check that that should be all of them. Of course, that doesn't add up to 24, so there must be other permutations left. Well, the other 3 permutations end up looking like this. Products of disjoint transpositions, or disjoint 2 cycles, 1, 2, 3, 4, 1, 3, 2, 4, and 1, 4, 2, 3. Count them up, we got 24, so we have everything in the group. So half of 24 is 12, so we want to find a subgroup consisting of 12 elements. We know we need to have this trivial subgroup, the identity element at least. And I guess maybe we want H intersect S3 to give us what we had before. Why not? Maybe that'll help us. So that means we want these 2, 3 cycles. And how about let's have that be true for intersecting with S sub x, y, z for any 3 elements. In other words, let's decide you decide to fix one of your numbers. And look at all the permutations that fix that number. And permute the rest. Then you're going to get a subgroup in a smaller symmetric group. And we want our subgroup to be order 3. Well, then that means we want all these 3 cycles. Well, it turns out that's 9 elements. That's not 12. So we need something else. But then we remember you need to have a subgroup. So we need to see what happens when you multiply any 2 of these elements. And it turns out, and you can check it for yourself, that if you see what happens when you multiply all these elements together, you will also get these 3. And this ends up being a subgroup, as we will prove, and consisting of 12 elements. I know what I'm missing. I looked at this and went, wait, this isn't 24. I'm missing 4 cycles, aren't I? So how many 4 cycles are there? Well, it turns out there should be 6. 4 cycles. Every 4 cycle has to have a 1, so put 1 in the beginning. And then after the 1, you just have a permutation of 6 possible symbols in all possible ways. All right, turn my brain on. Let's see, 4, 3, 2. Yes, I also have a procedure for generating all these as well. And that's the remaining 6. Okay. It turns out none of these are in the subgroup anyways. So you end up with 12 of the permutations in, and 12 of them are not. You can imagine using this approach in general would be very, very time consuming to go to higher SN. So then you start to look at this and see if you can't find any patterns. Well, we didn't include these 2 cycles. The elements here are products of 2 cycles, and it turns out any 3 cycle can also be written as a product of 2 cycles. Namely, A goes to B, B goes to C. You can see as you read from left to right that A goes to B for sure, B goes to C, and then C goes to B, B goes to A. It works. And you can check that these 4 cycles, if you try to decompose them as a product of 2 cycles, you'll always end up with a 3 cycle or more, something odd. So the ones that are not in the set are a product of an odd number of 2 cycles, and the ones that are in our subgroup are a product of an even number of 2 cycles. And thus we end up at the definition of an even permutation. So I'm going to let T sub n be the set of 2 cycles. These are called transpositions. And oftentimes the textbook talks about the word transposition, and I guess it's good to actually have the notation here. We're going to say that a permutation is even if you can write it as a product of an even number of transpositions. Note, these are not disjoint 2 cycles. They're just 2 cycles. So an even number of 2 cycles. let A sub n be the subset of even permutations. It turns out this is a subgroup of Sn and is called the alternating group. And so there's the answer to our question. It turns out to be a subgroup, and we can prove later that it actually has exactly half the elements in the symmetric group. So, and here's the proof that it's a subgroup. Let sigma and pi be two elements in this set. What does that mean? Well, by definition, it means that you can write sigma as a product of an even number of transpositions, and you can write pi as a product of an even number of transpositions. In other words, there exists sigma 1 through sigma 2k, pi 1 through pi 2r, all transpositions. So sigma is this product, and pi is that product. Well, gee, what happens when you multiply them together? You get sigma 1, you just multiply everything together. And how many terms are there here? There's 2k plus 2r terms. You can factor out the 2, and look, that's an even number. So sigma times pi is also a product of an even number of transpositions. Note, we aren't making any claims about whether or not cancellation happens. We're just saying that there exists a factorization. We don't care if there's repeats. Likewise, what happens when I invert? Well, what happens when you invert a product? You get the product of the inverses in reverse order. So instead of going sigma 1 to sigma 2k, you're going sigma 2k down to sigma 1 with the inverses. But a transposition is its own inverse, so I didn't bother writing the minus ones. So look, sigma inverse is also a product of an even number of transpositions. Therefore, sigma inverse is also an AN. So AN is a subgroup of Sn. So now I'm going to state a theorem that the textbook proves and takes a lot of effort to prove. However, the proof isn't useful for the rest of the course, so I'm actually going to skip it for once. It states that, well, this is the more important version, but the main step in the proof is the first part of the theorem. If you factor the identity element as a product of transpositions, then the number of transpositions that appear is even. And you can use that to prove the following fact. If you have a decomposition of sigma, in other words, you've expressed it as a factorization of transpositions in two different ways, so tau 1 through tau k and pi 1 through pi r, where these are all transpositions. Then it turns out that k and r are congruent mod 2. So you might remember from grade school that when you factor a number, it's going to factor uniquely into a product of primes up to ordering. You don't have that result for the symmetric group when you're factoring into transpositions. This is saying you don't even have uniqueness up to the number of factors appearing. What it does tell you is that you're either going to get always an even number of factors or an odd number of factors. You're never going to get both possibilities. So that's what this statement is saying, which is kind of important because the way I defined the alternating group was that you could write sigma as a product of an even number of transpositions. What this theorem states is that if sigma is an element of the alternating group, then every factorization of it into transpositions must have even length. And you might say, why do I care about that? Well, I can define a function, let's call it f, from an to the complement of an by taking f of sigma and just multiplying sigma by the transposition 1, 2. So according to this theorem, because sigma is in AN, sigma must be able to be written as a product of an even number of transpositions. That means f of sigma is a product of an odd number of transpositions. Because I tacked one on. More importantly, but based on this theorem, that means any factorization of f of sigma must also be odd in length. Therefore, f of sigma is in fact not an element in AN. So this codomain is correct. More importantly, there's an inverse function. Given by doing exactly what you might think it should do. Multiplying on the right by 1, 2 inverse, which means multiplying on the right by 1, 2 again. That's going to take an element that has an odd, can be written as a product of an odd number of transpositions, and give you an element that's written as an even number of transpositions. You can check that this is a bijection, which means that the number of even permutations is equal to the number of permutations that aren't even, or you could say the number of odd permutations. So that means twice AN is n factorial. Ergo, our group really does consist of half the permutations, as we wanted. We're not going to do as much in this course with the alternating group as one might in other more advanced math courses, but it turns out this is actually a famous group in group theory with lots of important applications. It turns out to be one of the main reasons why there's no quintic formula, for instance.